Welcome to the deep dive. It's Christmas Eve.
Oh, wow.
I know, right?
Yeah.
And I can't think of a better way to spend it than by unraveling some fascinating physics with you.
I like it.
So tonight, we're taking a deep dive into the mind-boggling world of light and matter,
Okay.
specifically their dual nature.
Dual nature.
Yeah, how they can act like both waves, either particles.
Right.
We'll be using Chapter 11 of this physics textbook that you provided to trace the steps of how scientists wrestled with this seemingly impossible concept.
It's a journey that really revolutionized our understanding of the universe.
Oh, absolutely.
At its most fundamental level.
Like at the tiniest level.
Yeah.
And you know what's really wild is that this whole mystery starts not with light itself, but with the discovery of a tiny, tiny particle, the electron.
That's right.
Yeah.
Back in the late 19th century, scientists were experimenting with something called cathode rays.
Cathode rays.
Yeah, they were basically shooting electricity through these tubes filled with gas at low pressure.
Oh, this is zapping these tubes.
Yeah, basically. They noticed a strange glow on the glass opposite the cathode, which is the negative electrode. It was J.J. Thomson who, through some clever experiments using electric and magnetic fields, figured out that this glow was caused by a stream of negatively charged particles.
Particles, huh? So is this like the birth of the electron?
You could say that these particles were zooming incredibly fast, almost at the speed of light.
Wow.
And this. Similar particles seem to be emitted by heated metals and even metals hit by UV light. So it was a clue that these weren't just some random thing from the experiment, but something much more fundamental.
Wow, so these tiny particles were popping up everywhere.
Yeah.
There had to be something important going on there.
Exactly. And then came R.A. Millikan and his famous oil drop experiment.
Famous oil drop experiment.
Yes. And he definitively proved that electric charge comes in tiny, indivisible packets.
Hold on. So just like an atom is the smallest piece of an element.
Yes.
This charge was the smallest unit of electricity.
Precisely.
Like the tiniest bit of zap you can have.
The tiniest. And the charge of those mysterious cathode ray particles turned out to be exactly one of these fundamental units. This solidified the existence of what Thomson called the electron, confirming that it was a real independent particle.
So scientists now had this tiny, negatively charged particle, the electron, which seemed to be a key ingredient in matter. Where does light come into the picture?
Well, that's where things get really intriguing. It's all thanks to a phenomenon called the photoelectric effect.
Okay, let's unpack this.
Sure.
What exactly the photoelectric effect?
Imagine shining a light on a metal surface. What do you think would happen?
Well, I know light carries energy, so maybe the metal heats up.
That's right.
Or maybe it reflects the light, like a mirror.
Those things do happen.
Yeah.
But sometimes something else occurs. That's quite unexpected. The light actually knocks electrons loose from the metal, causing them to fly off.
Wait, so you're telling me that light can actually knock electrons loose?
It does.
That's mind-blowing. I never thought of light as having that kind of power.
It is pretty amazing, isn't it?
Yeah.
And it gets even more bizarre when you look at the specifics. Scientists found that more electrons were ejected when the light was more intense.
That makes sense. Brighter light, more energy to knock out electrons.
But here's the kicker. The maximum energy of those ejected electrons. It didn't depend on the light's intensity at all.
Really?
It was determined only by the light's frequency, which relates to its color.
Hold on. Are you saying that a dim blue light could actually kick out electrons with more energy than a super bright red light?
It's true.
That doesn't seem right.
And there's another weird thing. For each metal, there was a specific frequency below which no electrons were emitted, no matter how intense the light was. This was completely baffling. From the perspective of the wave theory of light, which was the prevailing understanding at the time.
So it sounds like scientists had hit a wall.
They had.
Yeah. The way they understood light just couldn't explain what they were seeing with this photoelectric effect.
Exactly. The wave theory would predict that more intense light, regardless of its frequency, should always be able to kick out electrons. But that just wasn't happening. They needed a new way to understand what was going on.
And that's where good old Einstein steps in, right?
He does, doesn't he?
Always shaking things up.
And in 1905, Einstein proposed a revolutionary idea. What if light wasn't just a wave?
Okay.
What if it also came in tiny, discrete packets of energy?
Tiny packets of light. What did he call them?
He called them photons.
Photons, okay.
Yeah, he said each photon carries an amount of energy directly proportional to its frequency.
Okay.
So a blue photon, which has a higher frequency, packs more energy than a red photon.
Okay.
Even if the red light is much brighter overall.
So it's like each photon is a tiny bullet of light.
Yeah.
And it's the energy of that bullet that determines whether an electron gets knocked out.
Yes.
Not how many bullets are hitting the metal.
Exactly.
That's pretty wild.
You got it. This idea of quantized light energy completely changed the game.
Changed the game.
Yeah.
Okay, so Einstein comes along and says, light isn't just a wave.
Right.
It's also these little packets of energy called photons.
Yeah.
And that explains this photoelectric effect.
Yes.
That was driving scientists crazy.
It was. It was really a big problem.
Yeah, but where do we go from there?
Well, Einstein's insight, it really opened up a whole new way of thinking about light.
Okay.
He even came up with an equation to describe the photoelectric effect, showing how the energy of the photon relates to the energy of the ejected electron.
Okay.
It was a beautiful solution, very elegant, explained the observations that the wave theory just couldn't handle.
I bet this idea of photons had, like, a ripple effect throughout physics.
Oh, absolutely.
Yeah.
But the story gets even more mind-blowing.
Oh.
You see, a young physicist named Louis de Broglie started wondering if the opposite of what Einstein proposed might also be true.
Hold on. You're saying could matter, like the stuff we're made of, actually act like waves.
That's exactly what de Broglie proposed. He hypothesized that every moving particle has an associated wavelength.
The wavelength.
She called it de Broglie wavelength.
De Broglie wavelength.
And get this, the wavelength is inversely proportional to the particle's momentum.
Okay, break that down for me.
Sure.
Momentum, that's basically how much oomph something has when it's moving, right?
You got it.
Like a bowling ball has more momentum than a tennis ball.
Exactly.
Yeah.
So what de Broglie was saying is that the faster something moves, the shorter its wavelength.
So a speeding electron would have a tiny wavelength.
Yes.
But what about something big? Like a car?
It does.
Does that have a wavelength too?
Well, but think about it.
Yeah.
A car has a huge mass.
Right.
And it moves relatively slowly compared to an electron.
Okay.
So when you plug those numbers into de Broglie's equation, the resulting wavelength is incredibly tiny.
Okay.
Much smaller than an atom.
So that's why we don't see cars.
Exactly.
Or people, like diffracting like waves.
Exactly.
Right.
But with an electron, which is super tiny and can move incredibly fast, the wavelength is much larger, comparable to the size of an atom.
Okay.
That means it's actually detectable.
So we're talking about electrons.
Yes.
These tiny particles that we thought of as solid things. Potentially acting like waves.
And this idea wasn't just some theoretical curiosity.
Okay.
It had huge implications for how we understand the atom itself.
Now you've got me really curious. How did this idea of matter waves change our picture of the atom?
Well, before de Broglie,
the
most popular model of the atom was the Bohr model.
You remember that one, right?
Electrons orbiting the nucleus in neat little paths.
Like planets around the sun.
Exactly.
Yeah, I vaguely remember that from school. Though it always seemed a little too simple to be the whole story.
You're right.
Yeah.
It was too simple.
Okay.
The Bohr model couldn't explain a lot of the things scientists were observing.
Like what?
Well, for example,
Yeah.
why didn't those orbiting electrons just lose energy and spiral into the nucleus?
Yeah, that's a good question.
And why did atoms emit light only at very specific frequencies, creating those distinct spectral lines?
So the Bohr model had some serious flaws.
It did.
How did matter waves help?
Well, de Broglie's idea provided a crucial piece of the puzzle. If electrons could behave like waves, then maybe their behavior inside the atom wasn't about these neatly defined orbits, but about something else entirely. Standing waves.
Standing waves, like when you wiggle a rope.
Exactly.
And it makes that that up and down pattern.
Exactly. Imagine a guitar string.
Okay.
When you pluck it, it vibrates, right?
Yeah.
But it can only vibrate at certain frequencies, which create specific notes. Those are standing waves, waves that are confined and only exist at certain wavelengths.
I'm starting to see where you're going with this.
Okay.
So you're saying that electrons in an atom are like standing waves.
Exactly. They're confined by the electric pull of the nucleus.
Okay.
And this confinement restricts the possible wavelength and therefore the energies that the electron waves can have.
So instead of electrons whizzing around the nucleus like little planets, we should picture them more like these fuzzy waves, only existing in specific patterns dictated by the nucleus.
That's a great way to visualize it.
Okay.
And this concept of quantized electron waves explains those mysteries that the Bohr model couldn't.
Right.
The fact that electrons can only exist at certain energy levels explains those distinct spectral lines.
Okay.
When an electron jumps between energy levels, it emits or absorbs light at a very specific frequency.
Wow. So de Broglie's hypothesis about matter waves wasn't just some abstract idea.
No.
It actually solved some major problems.
It did.
And led to a completely new way of understanding the atom.
A much better way.
Yeah. That's pretty amazing.
It really is. And this new understanding where electrons exist as these probability waves spread out in space is the foundation of what we now call quantum mechanics.
Quantum mechanics. It sounds so complex and mysterious.
It is a strange world.
But I have to say, I'm finding it incredibly fascinating.
Good.
So what are some of the implications of this whole matter wave thing?
Oh.
Did it change anything beyond our understanding of atoms?
Oh, absolutely. It wasn't just about atoms.
Okay.
It had a huge impact on technology. And our ability to see the world in new ways.
Like how?
Well, for example, electron microscopes use the wave nature of electrons to magnify objects millions of times smaller than what's visible with a regular microscope.
So our understanding of the dual nature of light and matter isn't just some abstract theory. It has real-world applications.
Definitely. It revolutionized fields like materials, science, chemistry, and even medicine.
Wow.
But beyond the practical applications, I think the most profound implications of this discovery are philosophical.
How so? What kind of philosophical questions does this raise?
Well, think about it. We humans like to put things into neat categories.
Right.
We see something as either a wave or a particle.
Yeah.
But nature doesn't seem to care about our categories.
Really doesn't.
Light can be both a wave and a particle.
Yeah.
Matter can be both a particle and a wave.
Right.
It all depends on how we choose to observe it.
It's like nature saying, I'm much more complex than you think.
Exactly. And this duality challenges our very notion of what reality is.
Yeah.
What does it even mean for something to be a wave or a particle?
Right.
If it can be both.
Yeah.
And if the way we observe something influences how it behaves, does that mean there's no objective reality out there?
Whoa. Those are some deep questions.
They are.
It's like suddenly the world isn't as solid and predictable as I thought it was.
Yeah.
It's more fluid.
That's a great way to put it. And these are the kinds of questions that continue to fascinate physicists and philosophers to this day.
Wow.
It's a reminder that even though we've learned so much about the universe, there are still profound mysteries to unravel.
So we went from discovering the electron to uncovering the photoelectric effect and Einstein's brilliant idea of the photon.
And from there, we saw how de Broglie's hypothesis about matter waves completely revolutionized our understanding of the atom.
Yeah, it's amazing how these seemingly separate discoveries are all connected.
It is.
Like pieces of a puzzle fitting together.
It really highlights the interconnectedness of the universe, doesn't it?
It does, yeah.
Each discovery building upon the last, leading to a deeper and more nuanced understanding of how things work.
I've got to say, this deep dive has been one of the most mind-expanding experiences in a long time.
I'm glad.
It's made me realize how much I don't know.
Well, that's the beauty of science, isn't it?
Yeah.
The more we learn, the more we realize how much more there is to discover.
That's true.
But for now, let's try to summarize some of the key takeaways from our exploration.
Yeah, let's try to distill all this incredible information into some bite-sized nuggets of knowledge.
Okay, so first and foremost, we've learned that light and matter defy easy categorization.
Right.
They can exhibit properties of both waves and particles.
Yeah.
A concept known as wave-particle duality.
It's almost like nature's playing tricks on us.
Yeah.
Refusing to be confined to our neat little boxes.
I think it's more like nature showing us that our way of looking at the world might be too limited.
Okay.
The universe is far more complex and wondrous than we often give it credit for.
It's not just about light being weird. It's about matter being just as strange.
Exactly. Even the seemingly solid objects around us,
Yeah.
the chairs we sit on, the devices we use, they're all ultimately made up of these tiny particles that exhibit wave-like properties.
Right.
It really blurs the lines
Yeah.
between what we consider solid and empty space.
This whole idea makes me wonder if we'll ever be able to fully understand the universe
It's a good question.
if it keeps throwing us curveballs like this.
That's a great question, and one that scientists are still grappling with.
Yeah.
But I think the uncertainty is part of what makes it so exciting.
I have to agree. It's like we're on this grand adventure,
Yeah,
constantly uncovering new layers of reality.
exactly.
And who knows what incredible things we'll find next.
Exactly. And on that note, I want to leave you with one final thought to ponder.
Okay, hit me with it.
As we wrap up this deep dive into the mysteries of light and matter,
Okay.
we've explored how electrons, these tiny particles that make up everything around us,
Yeah.
can behave like waves.
Mm-hmm.
Now consider this.
Yeah.
If everything is ultimately made of these wave-like particles,
Right.
what does that say about the nature of reality itself?
Whoa.
Are we, too, in some sense, waves?
Whoa, that's a deep one. It's like,
Yeah.
are we all just vibrations in the cosmic symphony?
Perhaps. It's a mind-boggling concept,
Yeah.
and one that I encourage you to contemplate further. The idea that we might be more interconnected than we realize,
Mm-hmm.
that the boundaries between ourselves and the world around us might be far more fluid than we perceive,
Wow.
is both humbling and inspiring.
It really makes you appreciate the profound mystery and wonder of the universe, doesn't it?
It does.
It's a good reminder to never stop questioning and exploring.
Could have said it better myself.
Well, on that note, I want to thank you for joining me on this incredible journey through the fascinating world of light and matter.
You're welcome.
It's been an absolute pleasure.
The pleasure was all mine.
And to our listener, we hope this deep dive has sparked your curiosity and left you with a sense of awe at the profound beauty and strangeness of our universe.
Happy holidays, everyone!
Happy holidays, and may your curiosity continue to shine brightly in the new year.